Okay, let's now take this compact form of the solution of the one-dimensional wave equation and understand what each of these factors mean. Let's go from right to left in this case. Consider the meaning of the term theta, which does not depend on x or t, as well as a in this case, which does not depend on x or t. A is called the amplitude of the wave. This is something I am sure you have come across in some earlier studies, even in pre-university education. But this second term theta, which is independent of x and t, is often used but probably not so often physically interpreted. So, this is called the absolute phase or the initial phase. It is almost obvious to any student with a reasonable knowledge of trigonometry and calculus what the meaning of these two terms is. A, of course, is the maximum amplitude that the wave can take irrespective of what values of x and t there might be, whereas theta has a slightly more intricate meaning, but once again quite obvious if we understand these trigonometric functions well, which we should by now. For a wave with an value of theta is equal to 0 for the absolute phase, it simply tells us that the electric field amplitude E of xt at time t is equal to 0, right, has maximum amplitude because we are using the cosine function. That is, at this instant the instantaneous amplitude of the wave, which in this case is an electromagnetic wave and we are considering only its electric part, has the maximum value, attains the maximum value at x is equal to 0 for the instant t is equal to 0. Also at the same instant of time, which we label as t is equal to 0, for other values of x, the wave has a sinusoidal spatial dependence. Okay. Now, let us consider another example, that is the scenario where the initial or absolute phase has a value 2 pi over 3. Once again at the same instant of time, which we call t is equal to 0 now, we can note over here that at t is equal to 0, even at the value of x is equal to 0, this particular argument to the cosine function is not 0 because theta is 2 over 3. Therefore, the instantaneous value of the electric field at x is equal to 0 and t is equal to 0 is a, the amplitude multiplying cosine of minus 2 by 3. This essentially has the effect of the wave in some sense being shifted by a phase factor of 2 by 3 as this plot shows, and it certainly does not have a maximum amplitude at x is equal to 0 and t is equal to 0, and this essentially is the form of the wave. Okay. So, the effect of the initial phase is essentially to shift this wave around, and while the wave otherwise retains its spatial and temporal character. Okay. So, at first glimpse this absolute phase factor does not seem to have a great physical impact or implication. However, somewhat later in this course we will, in the context of laser pulses, and I will refer to this significantly later in the context of what we call few cycle laser pulses. This particular term, the absolute phase or the initial phase, will play an important role, and When we get there, I will make it a point to remind you about this very simple yet essential nuance which has a manifestation in attosecond physics in what you may call a somewhat surprising manner. Okay, there are more routine yet important characteristics of this wave, the light wave in one dimension, which we can go further and explore. Let us look at them. The cosine function is a periodic function. So, whatever argument we put into it will repeat for every cycling of the phase by 2 pi. This is something we know. So, we had in this case the cosine of kx minus omega t, right. So, let us take each of these variables one at a time. The spatial quantity of variable, which is x, and the temporal variable t, and examine the consequence of the fact that this functional form that we use to describe the wave here is a periodic function with a periodicity of 2 pi in its argument, right. So, let us plot at a given instant of time. Let us call the instant of time t is equal to t0, and to keep things simple we could even consider any instant of time and keep it fixed. So, we could even consider the instant of time t naught, that is t subscript 0 is equal to 0. So, we could even consider the instant t naught is equal to 0. If we do that, then at t is equal to 0, the wave is essentially described only by the cosine of k multiplying x. Remember, k we said was constant and did not depend on x, the spatial variable, or t, the temporal variable, right. Therefore, now if I simply make a plot of the cosine of kx, which is this red curve, t is fixed, this simply oscillates as we go away from x is equal to 0 to increasing values of x. This is a periodic function with a periodicity of 2 pi. So, every 2 pi units as the product kx increases in its value, the amplitude of the wave makes a repeat of itself. So, this length after which the waveform repeats itself periodically is called the wavelength. This is the parameter that informs us about the spatial periodicity of the wave, and this parameter is given the symbol lambda throughout literature, right. So, now every 2 pi the value of the argument kx repeats itself. As a consequence, the amplitude of the wave is the same for values kx plus or minus any integer, say n, multiplying a 2 pi, right. Now, the periodicity of the wave is therefore captured by the parameter that we introduced, which we have called k so far. And since the periodicity of the argument of the cosine function is 2 pi, k is 2 pi divided by this value lambda. That is to say, every time x goes from x to x plus lambda, the periodicity manifests itself because k multiplying lambda is just 2 pi. So, this gives us an insight into the physical meaning of k. It is essentially 2 pi divided by lambda. Related to this, there is another parameter which is very often used, especially by spectroscopists or in spectroscopy literature, which we call the wave number, that is given the symbol kappa here and is equal to 1 over lambda. Therefore, it has units of 1 over length. The relationship between kappa and k can also be written down correspondingly. Okay, what about the periodicity of the wave in time? Let us examine that. So, in order to do this exercise, let us fix our position of observing this wave. Let us fix the position to x is equal to x sub 0 or x naught. We could take x is equal to x naught to be 0, which is also equally good. So, if we did that, we would essentially have the following. The amplitude function E of x comma t would then be a multiplying cosine of minus omega t for x is equal to 0. Okay, so let us consider this scenario to understand the meaning of this important quantity omega, which we already know is related to k by the relation omega is equal to kV. Or omega by k is equal to V, right. We do the same exercise as we did for the spatial case. We fix the position and then make a plot of the amplitude of the wave as a function of t, time, and this amplitude essentially as time flows undulates from a maximum, goes through a 0 to a negative maximum and a positive maximum and so on, the cosine function being a periodic function once again. And now the periodicity of the cosine function essentially in terms of phase is 2 pi, and that translates in this case to a temporal periodicity of tau. We call the temporal period tau. That is to say, the amplitude, the value of the amplitude of the wave repeats itself at after every tau units of time ticking by, right. So, just as in the spatial case, we then realize that the argument to the cosine function, the argument to cosine of omega t essentially is the same as cosine of omega t plus 2 pi. Therefore, if I define tau to be 2 pi divided by omega, then I would have cosine of omega t is equal to cosine of omega t plus omega tau. So, that is the temporal periodicity of the wave. So, omega is given the name angular frequency because the argument to a cosine function is an angle. The units of angular frequency is radians. The SI unit of time is a second. The standard international unit of time is a second. Therefore, omega is measured in radians per second. Now, there is another form of frequency that we encounter in literature, which is the simpler parameter, which is 1 over the temporal period or time period of the wave, 1 over tau, and this variable is given the symbol nu very often in literature. So, nu is what we call frequency. So, nu is 1 over the time period, and obviously now since we have two interrelated quantities which are defined using the periodicity of the same cosine function, we have a relationship between nu and omega. Nu is omega divided by 2 pi, or omega is equal to 2 pi times nu. So, now let us just take a breather and look at what we have done so far. We have defined essentially wave as a propagating phenomenon. Further, we took a functional form that aptly describes the propagation of a wave, although it was somewhat idealized. A propagating wave is described by a function in the case of one spatial and one temporal dimension, by a function which has argument of the form x plus or minus vt, where x denotes the spatial variable, t denotes the temporal variable, and v is the constant velocity of the wave, the magnitude of the velocity of the wave. Then we essentially figured out that this functional form solves the differential equation in x and t, which is d2f by dx2 minus 1 by v square multiplying d2f by dt2 is equal to 0, where these denote the partial derivative with respect to the corresponding variables x or t. Then we adapted this to the context of light waves, which are electromagnetic waves. The amplitude relevant in this case, the spatio-temporal amplitude that is relevant in this case is E. E is a function of x and t, and we wrote down the simplest form of the wave of the light wave in one dimension to be E of xt is equal to a cosine kx minus omega t, after introducing another constant which generalizes the scenario so that the periodicity of this wave can be varied in space and time as the case may be. The spatial period of this wave is called the wavelength, which is popularly given the symbol lambda. K is 2 pi divided by lambda, and k is actually called the propagation vector as well, which we will see a little later. This would be the magnitude of the propagation vector. Kappa is the wave number, it is 1 over lambda. Likewise, the temporal periodicity of the wave is captured in the temporal period or the time period of the wave, which we denote by the symbol tau here. And omega then is the angular frequency of this wave, defined by omega is equal to 2 pi divided by tau. The cyclical frequency, or simply the frequency or the temporal frequency of the wave, is nu, which is 1 over tau, and therefore omega and nu are related as nu is equal to omega by 2 pi. Omega has the units of radians per second, and likewise nu has standard units of per second, or it is also given the name hertz, abbreviated as headset, things that you probably already are aware of. Something that may be new to some of you or for some of you is the interpretation of the additional phase factor theta, which again does not depend upon space or time, just like A does not depend on space or time. That is the quantity we call the absolute phase or the initial phase, here given the symbol theta. Theta essentially determines what the state of the wave is when x and t take the value 0, that is x is equal to 0 and t is equal to 0. In this case, if theta were to be 0, then the amplitude of the wave, considering the fact that we are describing the amplitude by the cosine function, assumes a maximal value at x and t both being 0, or if for an example we considered a value of theta to be 2 by 3, then it won't be the case, and so on. So we now have sort of the complete description of an idealized one-dimensional propagating electromagnetic wave and its simplest solution, where the amplitude of the oscillating electromagnetic wave is defined using a cosine function.